Hello students, welcome to your physics lab class. Now today we will be continuing our discussion on the measurement of band gap of a semiconductor using the 4-probe method. Now in earlier lectures on this particular experiment, you have learnt the theory behind the experiment in great details. So in the present class, what we will be primarily discussing is how we can perform the experiment through virtual lab, how we can obtain the data, how we will write down our observation in a chart, then how we will do the corresponding analysis, and finally how we will draw a graph out of the data using Excel. So let's begin. So what you see on your screen at the moment is the virtual lab site, Amrita Virtual Laboratories. This is the site that we will be using in order to perform our virtual experiment. Now, in this page, as you see, there are various experiments of physical sciences. But the experiment that we are at present interested in, that is under the category of solid state physics virtual lab. Solid state physics virtual lab. And the experiment, as you see, is over here, resistivity by 4-probe method. So we will click on that. And the corresponding virtual lab based experiment opens. So you have already understood the theory, procedure, etc. So we will straight go down to the simulator. Here you see you have the setup as was described to you. You have the oven within which your germanium semiconductor chip is placed, and on the chip, of course, the leads of the 4 probes are touching, 2 voltage probes and 2 current probes. And this oven is connected to this oven control, using which you can control the temperature of the oven. Here is the digital microvoltmeter, which will note the voltage, and here is the constant current source. So here you see other parameters that you can adjust. Here within the material you can choose germanium or silicon, but since we are interested in measuring the band gap of germanium, we select germanium. Range of current, will keep it to 20 milliamperes because we are interested in fixing the current somewhere between 2.5 and 3 milliamperes. So for present purpose, I will keep the current to say 2.8 milliampere. I fix the current at 2.8 milliampere. Okay. Now, what I want to do is to set the temperature. Be careful at this point. Here the temperature is quoted in degree centigrade. It can go from 25 degrees centigrade to 95 degrees centigrade. Okay. So we will be increasing the temperature in steps of 5 degrees centigrade. we will go from 25 degrees centigrade to 95 degrees centigrade in steps of 5 degrees centigrade. So the first reading that we will take is at 25 degrees centigrade, but I am showing you the first reading at 30 degrees centigrade. So for what we will do is we will press the set button. That gives us the flexibility to alter the temperature, and we will increase the temperature over here to 30 degrees centigrade. So for you, this will be the second reading because the first reading is at 25 degrees centigrade. Then after setting the temperature, I started from 30 because I wanted to show you how to set. In order to do a 25 degrees centigrade run, you do not have to set the temperature because the initial temperature is already set to 25. So first temperature is set to 30 degrees centigrade. Then I'll press. So now your oven is at 30 degrees centigrade. And the current is kept constant at 2.8 milliampere. You know, throughout the experiment, the current will be kept at a constant value, and we have chosen that value to be 2.8 milliampere. Now we will run the setup. Okay, and we will change the range of the voltmeter to 100 millivolts so that the appropriate voltage can be captured by your microvoltmeter. Now, when we run the setup, we see that at 30 degrees centigrade, the voltage that is displayed by your microvoltmeter comes to 79.48 millivolts. 79.48. That is your voltage. Okay. Next, what do we do? Next, we will take the reading for the next temperature. So we will press on reset. Okay. So that the system goes back to its original setting. Next, the current is at 20 milliampere. Range of current. Our current is kept fixed at 2.8 milliampere. Pressing set, we adjust the temperature to 35 degrees centigrade. After 30, it's 35 degrees centigrade. We change the range of voltmeter to 100 millivolts and again run. So you see the voltage in the microvoltmeter is decreasing with increase in temperature. But that is what you expect, because as your semiconductor chip is getting more and more heated up, its resistance is decreasing. Unlike that of a metal or a conductor, if you heat up a semiconductor, its resistivity falls off. You have been told about this in the theoretical discussion on the experiment, and that is what you experimentally see. Because the resistance is falling off, that's why the voltage, corresponding voltage, is falling off, because your current is fixed. So we will note down the temperature and the corresponding voltage for a constant current. This we will do for 15 values of temperature from 25 degrees centigrade to 95 degrees centigrade in steps of 5 degrees centigrade. Then what we will do is we will make a table. So I will share with you the table that we are going to make. So here you see on your screen the table that you are supposed to make. In your table, in the first column, you have temperature in degrees centigrade, which you note 25, 30, 35 till 95 degrees centigrade. In the next column, you will write the corresponding temperature in Kelvin. The corresponding temperature you will note down in Kelvin. Okay. After that, you will write the corresponding voltage that you find out from your voltmeter in millivolts. Okay. And next, you will calculate the resistivity, corresponding resistivity rho using the voltage that you have noted from your voltmeter in millivolts and the corresponding value of current at which you have kept the current to be fixed. Here it's written as 3 milliampere, but for our case, we have fixed it at 2.8 milliampere. You can fix it to any value between 2.5 and 3 milliampere. Okay. Then you can find the corresponding resistivity rho as voltage by current into 0.213. Be careful here, there's no need to change units because you already have the voltage in millivolts and the current in milliampere. Then you have the corresponding temperature in Kelvin. You will find 1000 by T in Kelvin inverse. And in the subsequent column, you will find log of rho. Log of rho to the base 10, log of resistivity to the base 10. And after that, what you will do is you will plot out a graph of log rho versus 1000 by T. 1000 by T along the x-axis and log rho along the y-axis. And I will show you how to plot a general graph in Excel now, so that you can do the entire thing on your computer. So I'll plot out a model graph in Excel. So suppose